Yeah, now tell me. So let me just repeat whatever I have done so far so that for the recording it is clear. So to find the breakaway or break-in point, what you do is you have open loop transfer function k times g of s h of s. Now what you do is 1 plus kg equal to 0. You have to equate that to find the closed loop pole, and then um, k should be on the one side, all other things should be on the other side. So find k as a function of s using the 1 plus kgh equal to 0, and then differentiate k with respect to s, and then find those values of s. So those give you the possible breakaway or break-in points. Whether they actually correspond to breakaway or break-in points depends. For example, if they are real, only then they can be breakaway or break-in points. If they are complex conjugate, ignore that, and also ignore the other values where k turns out to be negative. Okay, so and then based on an intuition, also intuitive sketch, also you know where to expect the breakaway or break-in point. Based on that, you decide whatever the breakaway or break-in point is. But the the derivative equal to 0 equation will give you the possibilities of the breakaway or break-in points. Okay. Yeah, you may continue your questions now.
Yes, sir. So next question was, yes, sir. So in this question, it's saying to compute the gain and phase crossover frequencies of the system.
Okay.
So I have calculated. So according to my understanding, gain crossover frequency is basically the magnitude of g omega, and uh, I need to equate that g of j omega equals to 1 and calculate for omega,
Yeah.
right? And for the phase crossover frequency, I need to uh, calculate the angle of j omega and equate it that to minus pi and compute for minus for omega.
Hmm.
Then how to compute the gain and phase margins?
So, what question are we talking here?
It is practice question 1. Practice assignment 7 question 1.
Okay, just give me some time. I will simulate first in MATLAB myself and get an intuition.
Okay.
Anything else on root locus on route levels? Other topics?
Let me just check once. Sir, in this practice assignment 5, what is the sensitivity?
There are lots of
Like
definitions for sensitivity, right? With respect to what?
in this question, if you can see this.
I will let you know. I will discuss with the other. I'll discuss and let you know. It's not clear, I guess.
Okay, okay. Okay, then.
Okay, let me tell you about the gain margin and phase margin definition. Okay,
Okay.
so um, so you have 1 plus kgh equal to 0, right? Where gh is open loop, correct?
Yes, sir.
So uh, so what happens is so okay, when the gain is 1 and the phase is 180-degree at a given frequency, then that means you are at the border of instability. Okay, so what you do is you find the gain crossover and phase crossover frequency, right?
Yes, sir.
Correct. So at the phase crossover frequency, you have 180-degree phase. correct?
Yes, sir.
Calculate the gain there. Calculate the gain there. So what is the gain
Okay.
at phase crossover frequency?
Okay, so that is the gain margin.
No, the amount of, so if you increase the gain, okay, let's say I'm not talking in decibel now. I'm talking in absolute values. Let's say the phase crossover frequency is let's say the phase crossover frequency is something, and the gain at phase crossover frequency is, let's say, 0.5. Okay, it means when you increase the gain twice, you will get one at that phase crossover frequency, right? And you'll get 180 degree at the same frequency, which will be instability, which will be the beginning of instability. So the gain margin is 2, because when increase twice, you get gain 1 at the phase crossover frequency, correct?
Yes, sir.
Same thing
Correct.
in organ decibel. Gain equal to 1 means 0 decibel, right? So if the if the gain at phase crossover is minus 3 decibel, the gain margin is 3 decibel, because when you increase gain extra by 3 decibel, then you'll get at that same phase cut crossover frequency, you'll get same frequency, you'll get 180 degree, and gain is 1. So the the gain at phase crossover frequency will give you the gain margin. Okay, the phase at gain crossover frequency will give you the phase margin. Okay, so for normally for the beginning of instability, you want gain 1 and phase 180 at the same frequency. You got it?
Yes, sir. Right.
So,
Which
but
basically means that whenever
can you allow me
instability
to
is
finish
about.
what I say? Can you allow me to finish what I say?
Yes, sir. Yes, sir.
So for the beginning of instability, you want gain 1 and phase 180 at the same frequency. But in generally, you won't. You will have the gain 1 at some frequency called the gain crossover frequency, and you will have the phase 180 at some other frequency called the phase crossover frequency. Both will not match. So to get them same Vatic, there are two options. One is you have the phase crossover frequency where the phase is 180 degree, and then increase the gain so that it reaches 1 at that frequency. So that will be how much you can do that till the gain hits 1 at phase crossover is gain margin. The other option is take the gain crossover frequency where the gain hits 1, gain is already 1. The phase will be something else, let's say minus 130. Now what you can do is you can increase the phase lag further of 50 degrees. You can introduce extra 50-degree phase lag until you hit that minus 180 at the gain crossover frequency. So that is the phase margin. Got it? Now you can ask.
Yes, sir. Right. So I was thinking like the whenever the system is about to go in the instability phase, this means that it is about to cross that imaginary axis, and
Yeah,
from left half plane, it is about to go into the right half plane.
yeah. So the thing
But
is, at the beginning of instability, you will have a purely imaginary root that satisfies 1 plus kg h equal to 0, right?
yes, sir. Right.
So that imaginary root will be something like j omega, j times something, call that omega something, j times omega.
Okay.
So which
Yes.
means you are putting s equal to j omega, right?
Yes, sir.
Correct? But putting
Correct.
s equal to j omega will means frequency response, correct?
Yes, sir. Correct.
So which means after frequency response, you will have a frequency at which the gain hits 1 as well as the phase hits 1 minus 180.
Right, sir.
But normally your system will not be unstable. The open loop system, normally Bode plot is done for systems whose open loop transfer function is already stable. Okay. Why? Because only then you can find the frequency response. If you excite an unstable system with a sinusoid, it will blow up, right? You can't determine this. It will not settle into a steady state, correct? So
Correct.
normally in Bode plot or your analysis, you assume this open loop system is already stable. You just want to know how much close to instability it is. So when the system is beginning to be unstable, what happens is you have a purely imaginary axis pole. So which means at the frequency response, you will have gain 1 and phase 180 degree at the same frequency. But since the system is already stable, at the same frequency, you won't have both gain 1 and phase 180. You may have a frequency at which gain is 1, but the phase will not be minus 180, then it will be minus 130 or something. You may have a frequency at which phase is minus 180, but the gain would not be 1 there. It might be 0.5 or something. So what you can have is when the phase is minus 180, which is the phase crossover, the gain is minus 3 dB, which means you have a 3 decibel margin, because when up to 3 decibel you can increase the gain. But if you increase to 3 decibel or more, you hit that you hit that point where you get 180 degree and one at the same time. Similarly, at the gain crossover frequency, where you have gain is 1 or 0 dB, the phase will not be minus 180. It's a stable system, right? So it will be minus 130, which means you have a 50-degree gap between minus 130 and minus 180. So the phase margin is 50 degree.
Right,
So the
sir.
gap between 0 decibel and the actual uh, gain at the phase crossover is called the gain margin, and the gap between minus 180 and the phase at gain crossover is called the phase margin. Okay.
Phase margin. Okay. And sir, one more thing in this. So in this particular week, body plot is there. If you can give some idea of body plot, it will be helpful.
Bode plot. Did you attend the live session on Friday?
No, sir,
By
and the recording is also not available, so I haven't seen that.
Okay, Friday I did Nyquist plot. So people there said Bode, they already watched the videos and have an idea. Only Nyquist plot is confusing. If you want me to repeat the Bode plot, I can do it. Not a problem. Give me 2 minutes.
Okay,
I'll
sure.
share the
Thank you.
presentation. So you want me to teach you what? How to draw Bode plots?
Yes, sir, body plots.
Okay, just a minute. What is the time now? 5:30. Okay, we still have half an hour. Okay. Which week it is?
Sir, it is week 7.
Okay, wait. I'm opening it. Give me some time. Just a moment. It's hanging a bit. don't know what.
And sir, like week 8
Just a
questions
moment.
are also.
Just a moment. Huh? What?
I was I was saying that week 8 questions, the grid assignment questions are also tough.
Compensator designer.
That no sir, the subjective grid assignment week 8.
So what's the topic that you're feeling tough?
Yeah, so that is I think those questions.
Compensator design.
Yes sir.
See, those long questions are for your assignments and practical application only. In your exams, you don't expect very long questions like that. Okay. In exams,
Okay.
you'll expect only conceptual questions that can be done in a reasonable amount of time in a multiple choice framework. Okay. So don't kind of uh, get scared and all. Yeah, I opened it now. Can you see my screen?
No sir. No,
Okay,
yes sir.
wait a minute. Yeah, so okay, I will teach from scratch or you want specific questions?
No sir,
If
you
you
just
need to,
start from scratch.
okay, then I will open my own document and type that.
Okay.
Can you see my document?
Yes sir.
Okay, it's loading. Give a moment. Increase the size. So let's take a simple transfer function. Let's say g of s is 1 by s plus 1. Just hanging. Wait a minute. So let's take g of s. Can you see what I'm typing?
Yes sir, it is visible.
So for frequency response, what you do is you put you are giving a sinusoidal input, right? So you put s equal to j omega, okay? Because e power j omega is purely sinusoidal, correct? Correct.
Yes sir.
So you get 1 by. So this will be your transfer function for a sinusoidal input, okay?
Okay.
So the magnitude of g is will give you the gain at that particular frequency omega. What's the magnitude of this guy?
1 over under root 1 plus omega square.
So now let me take 20 log m, okay? The 20 log of a given gain is called the decibel gain, okay?
Right.
Got it?
Yes sir.
Are you getting it?
Yes sir.
So what is 20 log of this?
So it will be
minus 20 log of 1 plus w square, right?
right minus 20 log of 1.
This minus 10 log of, sorry, you'll have a square root here,
Yes, sir. So it is minus 10 log of 1 plus omega square. Yeah,
correct?
right.
So now this decibel will be approximately, can I do this?
So if
When
omega
omega
is
is very, very high, when omega is very, very bigger than 1,
yes, sir, we can do this.
what will happen to this guy?
Yeah, so omega square plus 1 will become omega square.
So it will be simply what? Minus 20.
Minus 20 log omega.
What do you observe here?
So
So take
when
dB as y, and take log omega as x. What do you observe here?
it is a straight line with the negative
Which
slope of
slope?
20.
With slope of
20.
minus 20, right?
Yes, sir.
So you get what is happening here. So when omega is much bigger than 1, the decibel is actually falls linearly with
Okay.
increase in log of the frequency. Log frequency is called decade. Okay, the
Okay.
log of
Okay.
the frequency is called decade because uh, you know uh, if the frequency increases 10 power 0, 10 power 1, 10 power 2, 10 power 3, and so on. Okay, this log will be proportional to 0, 1, 2, 3, right?
Yes, sir.
So each of them is called a decade because it encompasses 1 power of 10. Okay,
Yes, sir.
so dB falls linearly with increase in decade at high omega. Got it?
Yes, sir. Got it.
When dB is, what happens when omega is really less than 1?
So it will be log 1, right? Which is 0.
Yeah, so it will just be constant, right? In general.
Right.
So what you do is asymptotically, if you plot a graph between decibel and decade, initially it will be constant and then later it will fall. Got it?
Yes, sir.
So let me actually show this in Octave. So So this is what a Bode plot is. The magnitude plot of a Bode plot basically plots decibel gain in decibel, which is minus 20 log, sorry, 20 log gain, and then the frequency input is in logarithm decibel, a decade logarithmic scale. It's called a decade. So let me Bode of cis. So do you see the diagram here? So initially you see it is constant, right? At low frequencies. So the cutoff frequency is 1, 10 power 0. When frequency is less than 1, it kind of is a constant. It value 0, decibel is 0. And then after greater than 1, it actually falls off with linearly. You see here?
Yes, sir. Right.
So what you do is you can approximate this Bode plot asymptotically as follows. You can have 0 until 1, and then after 1 you can immediately start decreasing by 20 dB. Okay, that is
Right.
called asymptotic approximation to the Bode plot. Got it?
Yes, sir. Got it.
Now what will happen when instead of 1 by s plus 1 I have 1 by 1 plus 2s? So here where is the pole? Where is the pole here?
So pole is basically at minus 1 by 2.
Okay, sorry. Instead of 2s, I will have 0.5s just for simplicity. What is the pole now?
Yes, sir. So it is minus 0.5. No, sir. 1 by 2,
No,
which is minus 2.
minus 2. Very good. So let me do g of j omega, which is 1 by 1 plus, correct?
Yes, sir.
Sorry, correct?
Correct.
So what is m?
Sir,
1
1
square
1
root
by 1
of
plus 0.5 j omega, right?
0.5. Square you get magnitude, you get 0.25, right?
Yes, sir.
Correct?
Correct.
And then what is the 20 log of this? 20 log m minus
So 20.
20 log 1 plus, got it?
Yes, sir. Got it.
So here when omega is much bigger. So here what you have to compare 1 and compare 1 and 0.25 omega square.
So by the way, it will be minus 10, right? You have
Sorry,
removed the
minus 10.
square root.
Sorry. Got it?
Yes, sir.
So when omega is really large, what do you get? Let me see compared to what it is large, but omega is really large, what do you get?
20 log. So it will 1 plus 0.25 omega square will be 0.25 omega square, and you can break that thing to log AB is equals to log A plus log B, which is
So what
log
will you get?
0.25. So we will get
Okay, I
minus
can do this minus 10 log of 0.5 omega the whole square, which will be minus 20 log of 0.5 omega, right?
right, sir.
It will be what? Minus 20. What is log of
Log
A
point
into B?
log A plus log B, log 0.5 plus log omega,
Minus.
20 log omega, log 0.5.
So it will be the same thing. The slope is similar, same minus 20, right?
Right, so it is a line with an
Right
intercept.
now, y, let's take y as decibel. So this is a decibel. And then x as log omega, which is the decade. So you'll have now y equal to minus 20x plus some constant, correct?
Right,
So the same thing except that, this part will attain later, okay? This falling of 20 dB will come after, it will not come at 0, which is frequency 1. Okay, here the log is 0, right? Log omega is 0, 10 per 0. Here the
yes, sir.
frequency will not start falling after 0, it will start falling after that. Let's now see after what it starts falling. So the condition for this is 0.25 or zero point 0.5 omega should be much bigger than 1, correct? That's the condition, right?
So omega must be much bigger than 1 by 0.25, which is 2.
So the cutoff frequency, what is the cutoff frequency? It's 2.
It's 2,
Cutoff
right?
frequency is the frequency at which after which the thing starts falling. So the cutoff frequency is 2, okay?
Yes, sir.
So the cutoff decade will be log of log of 2, okay? So if I plot the transfer function of this, let's call this 1 by 1 plus 0.5 s plus 1, correct? So let me call this. You see here,
Yes,
the
sir.
cutoff frequency is slightly after this. It is like this, here, somewhere over here. Got it?
Yes.
Now the advantage of this logarithm, similarly you can do for a 0. For a 0, what you can do is, if g of s is s plus 1 instead of 1 by s plus 1, what will happen is, there won't be a minus sign here. Got it? Correct? Because it's
Yes,
not in the
sir.
denominator anymore. So the
Right.
slope will be plus 20 dB. Correct?
Correct.
So it will start at constant and then increase with 20 decibel per decade. Got it?
Yes, sir. So basically, with
So
every zero, that slope will increase, and with every pole, that slope will decrease.
yeah, so the advantage of this is, let's say you have a bunch of let's say you have a bunch of let's say 1 by 1 plus st 1 plus st dash 1 plus st double dash divided by denominator you have, let's say 1 plus s, call this t triple dash 1 plus st 4 dash 1 plus st 5 dash, so on. Okay, so if you take 20 log, what will happen to all these guys? It will be additions of 20 log of all these things.
Yes, sir. Right.
So what will happen here? The Bode plot, the Bode magnitude plot of a complex system will be nothing but the sum addition. That's why we take log. Log transforms multiplication into addition.
Yes, sir. Right.
Each guy, right? So what you can do is, initially when the frequency is much less than all the cutoff frequencies. So cutoff frequency of this will be 1 by t, correct? Because the pole 0 is at 1 over t here, correct?
Yes, sir. Right. Right.
The cutoff frequency. So when the omega is much less than all the cutoff frequencies, the slope will be simply 0. It will start up at 0. And then for every cutoff frequency you encounter, it will increase the slope by 20 dB if it is a 0 and decrease the slope by 20 dB if it is a pole. Okay,
Right. But
got
sir,
it?
like I got it. But in the plot, what pole will be the first one? Like
You can
out
arrange the
of.
poles in descending order, right? And then see what is the first, correct?
Okay. Okay. Right.
But if you have a pole at 0, then the graph will start at 20 dB per decade only, correct?
Oh. Okay. Right.
You have g
Right.
of s is equal to 1 by s, then g of j omega will be 1 by j omega, and then m of j omega will be 1 by omega, right? So
Yes, sir.
20 log m will be minus 20 log omega. So it will always, y is equal to minus 20x. It always is at, it always is at 20. It starts with 20 dB decimal per decade slope.
Yes.
Similarly, if you
Right.
have 1 by s square, it will start with minus 40 dB per decade slope, okay?
Right.
Because the cutoff frequency is 0, right? And the log 0 is minus infinity. So the graph will start at minus infinity now with with slope minus 20 dB or 40 dB, whatever. Got it?
Yes, sir. Got it.
So this is why the body magnitude plot is very easy. You know, you find all the cutoff frequencies. You know, st- when you encounter every cutoff frequency, you know, increase the slope if it is 0, and decrease the slope if it is a pole. So and then this is the asymptotic approximation. Got it? And then
Yes, sir.
similarly, every pole will contribute. So here, if you look at the phase plot, what is the phase at asymptotically? When
It's
omega is
90
really
degree.
high, minus 90 degree, right?
Minus 90 degree. Yeah.
So every pole will contribute an asymptotic phase of minus 90 degree, and every zero will increase the asymptotic phase value by 90 degree.
Yes.
Got it? This is what Bode plot is all about.
Sir, but the interesting question is if the Bode plots are given and we need to figure out the transfer function from the Bode plot.
For that, what you do is, okay, that's very, you can start with 0, and then you can see wherever the frequency falls from this graph, you can see it starts falling somewhere over here, right? The slope
Yes.
starts falling to 20 dB. Roughly, you can find out. What you do is draw tangent lines to
Actually, I
this
have a
part where it's
example question.
falling, and draw tangent line to the constant part. See where they meet. That will be the cutoff frequency.
Okay. So
Okay, I
after
will
that,
open some. Oh wait, I will open Paint and see if I can explain that.
I have an example
Give
question.
me
If you
a
want,
moment. Wait, I will explain.
okay.
What you're asking is what I'm trying to say, right? So wait, hanging again. Wait. So let's say somebody gives you a Bode plot like this. Okay. What you do, you see the plot? Can you see the plot?
Yes, sir.
What you do is draw a tangent line, from here. Okay, this is 20 dB part. Now then this is a constant part. So where they meet, this guy, they meet here, right? Wait. They meet at this point here, right?
Yes, sir.
This is a
Yes,
cutoff
sir.
frequency and the pole location. Okay, this is where the
Okay.
pole is. Got it?
Yes, sir.
And this green part is called the asymptotic approximation to the Bode plot. Remove this. Remove this. So this green part alone, what you see here is called the asymptotic approximation to the Bode plot. It's actually a fairly good approximation. Okay.
So if you have like intersected this line, this is a pole, and in case of a zero, you have
Same thing
the
is
line up.
the only difference here is that in the case of a zero, you'll have a line like this to
Right, sir.
intersect.
Yeah.
Okay. If you have multiple poles, it will be, let's say you have two poles. Okay. So which means initially it will be 0 dB and then 20 dB and then 40 dB fall, right? So let me draw that. So let's say you have, so you'll have three asymptotic lines now. So one for this, then one for this 20 dB and then another for 40 dB. I'm not drawing it exactly, so I can't show, but you understand the principle, right?
Yes, sir.
Okay, let me, something like this it will be. So you will start here. So this will give you the first crossover frequency, and then wait, and this, and then do this. This will give you the second crossover frequency. Okay, this guy here, you get it?
Yes, sir.
You see where the two poles are?
Yes, sir.
One is over here, the other is over here. And if you remove all the unnecessary protrusions, you will get the asymptotic Bode plot. This part alone, all the asymptotic Bode plot. Okay, got it?
Yes, sir.
Anything else?
Yes, sir. So thanks for the doubt clarification. So I was just saying that if you after this we have a meet of for DSP. So if you have time, we can have one more meet today itself after 7, if possible.
Today,
Based on
not possible.
okay,
Friday only we can meet next time, right?
okay. So I was just
Any
asking
other?
for a lead lag compensator meet,
You can either ask on Friday or you can ask in the WhatsApp group.
the G space.
You can ask in the WhatsApp group itself.
Okay, okay. That WhatsApp group. Okay.
Yeah. Shall I break for now?
Yes, sir. Thank
Okay.
you, sir.
Thank you.
Sure, sir.